I think because this would be the last lesson on lines in space, I would write some problems for you and wait a little bit for you to see how you can solve those problems. And then I will probably give you the last part, and then we will be finished, okay, for this. So I will start writing some problems on the board. These are interesting problems, and I really expect you that you should be able to solve them. Okay, so let us see how it goes. Okay, so I give you some time. I hope that you can solve these problems. They're algebraically not involved, but I want to see how you think about the problem. So you can also refer to your notes if you have any, and then try to solve these problems. Then I will continue my lesson, and then we are done for this section. Okay, how did it go? You are waiting for a new one? You finished?
I'm thinking.
Okay. The geometry is not that complicated. Yes? You have a plane for the trace problem, you have a point, you know the mirror image is very clear. You want to find it. It shouldn't be hard.
Men det beror på ifall den är över som och en sida. Jo, men du flyttar normal vektor till.
Okay, so if you don't mind, let us start solving them, because it might be I want to complete the lesson after a while. So, what is your opinion so far about the first one? So you have, if you want to do this, you go to a scratch paper, you sketch something for yourself. So you have a plane, you call it P, and then you have a point somewhere, and afterwards it is clear that this point does not lie on the plane, because that would be extremely simple. Then the reflection becomes itself. Yes, if it is on the plane. So it is not on the plane, and we are supposed to find its reflection with respect to this one. So you draw a perpendicular line, and then continue it as to its length. Whatever this length is, you do the same thing. You get a point, so let us call it A prime. The point is to determine this. That's the meaning of the question. Okay, so how did you think about the problem? No clue? You're just a strategy. Yes?
I was thinking that I could extend the normal vector all the way to A, or shorten it, depending.
We don't have that control over the normal vector, because what you can read is one normal vector, and of course you can multiply it by any number. I don't understand what you mean by extend it, because you read one normal vector 3, 2, 1, and if I tell you where it is, of course there is no location associated with the vector. If you want, you can draw it exactly from here in your head, but how long it is, we don't know, unless you start measuring the distance from this point to the plane and try to do something to measure these things. You are making things complicated. But what is the core? If I want to find A prime, I would focus in finding something else first. What is that? I will try to find the coordinates of this intersection. Because if I know this, then I can find this. How? Because this is in the middle, this becomes the x-coordinate of the h is the x-coordinate of this plus that divided by 2. I already have the x-coordinate of A. If for some reason I can find the x-coordinate of h, then using that I can find the x-coordinate. And I can do the same thing for y and z. So I would recommend you to try to find h. But how can I find h? H is what? H is intersection between two objects. One object is the plane and the other object is that line. So if you want to find the intersection of two objects, you need to have the equations of two objects. You already have the equation of one of those, which is the plane, So you will focus yourself on finding an equation for line A prime. This is the way that you have to think. And then you ask yourself, how can I find an equation of a line? If you have listened to what I said, I need two pieces of information for writing an equation for a line. What you need 1 point on it, which you have it. A is 1 point on the line. And then you need the direction vector, which means you need a vector that is parallel to your line. But then immediately it becomes clear that the normal vector of the plane plays the role of the direction vector of your line. So that's it. Yes? So what you do, you say that, okay, the normal vector of the plane is equal to 3, 2, 1. This means that the direction vector of the line A prime, for example, is also the same thing. Yes? And I want to find an equation for the line. You can write it as a canonical form. You can write it as parametric form. I would prefer to write it in parametric form. That's easier. So then what I do, I would write that the line A prime has x equals to y equals to z equals to. X is what? This component times your parameter t plus the x coordinate of one of the points that you know it's on the line. So that's plus 2. And then what I do is 2t plus the second number 1, and this one is t plus again 1. This is the equation, an equation for my line. I already know an equation for my plane. So to find an intersection point, what I am supposed to do, I have to set up a system. So one part of the system is equation for my line. Another equation is equation for my plane. Okay? And I have to solve this to find x, y, and z. I can also find t, but probably t is not that important for me. But how many equations are involved? 4. And how many unknowns you have? X, y, z, and t. 4. So that is enough. But this system is very, very simple because x is written in terms of t, y is written in terms of t, z is written, so I can replace, then I find t. When I find t, I substitute here, I find x, y, and z. So let me just do that. If I put this here, let us do it in our head. I have to multiply this by 3. This becomes 9t plus 6 plus. I have to multiply this by 2. It becomes 4t plus what? 2. And I have to write z itself. It's equal to 20. 90 plus 40 plus t is 14t. And then 6, 2, and 1, how much is that? 9. I move it the other side. Yeah, good. It becomes 14. And then t becomes what? 1. But when t becomes 1, this means that x becomes what? 5. Y becomes 3. And z becomes 2. So this means that now I know the coordinates of this point. So h is what? 5, 3, and 2. But on the other hand, I know that the x coordinates of h is also equal to the x coordinates of a plus the x coordinates of a prime divided by 2. Yes? Because that is the middle one. We had this before. But x coordinate of h, I got it. It is 5. X coordinate of a is already given. It's 2. X coordinate of a prime is missing. There's only one missing part. So 2 times 5, 10, minus 2 is 8. So x of a prime is 8. And then you can do the same thing. So I would write an equation for y. So what is y? It's 3 is equal to the average. What is y here is 1. Y of a prime is missing. So this means that y a prime is actually 6, 5. Okay, and then we will go to the next one, 2. Z is 1 again. Z of a prime divided by 2. Am I right or not? Yes. So it becomes 3. So z of a prime becomes 3. So then finally, if I ask you what the point a prime is, you found it. Yes, it's 8, 5, and 3. That's the point. Yeah, is that clear? So it was not hard. I mean, the geometry was very simple, but of course you need to get some experience. You need to broaden your perspective. I think I was also checking on GeoGebra. That's also good to check it on GeoGebra to get a feeling of what is going on. So I go to 3D graphics. I usually prefer have these grids on. So the x-axis is the red one, the green one is y, and the other one is z. Okay, sorry, this is left behind the curtain. So can you just read me what was the equation for my plane? What was that?
3x.
3x plus
2y
2y
plus z.
Z equals to
23.
23. Okay, so this is my plane. So if I want to see it from different perspectives, so that is my plane. Yes? And now, what was the point? A was equal to what?
2, and then 1, and then 1.
And then 1. So that's also the point A. So this is the situation in a space. Yes? And then the nice thing in GeoGebra is that you see have this feature. You don't need to do anything. So you go here and reflect about plane, and then you go choose your point and choose the plane. It gives you 853. So actually we did it correctly. So that was the answer we got, yes? So that is 8, 5, and 3. Okay. I want to keep this the same, but I want you to, now I think you have a lot of experience for the second one, because the second one is now we want to reflect about a line. Okay, here I wanted to reflect about a plane, but, okay, so let me just pause the recording. Okay, so the next problem, oops. The next problem, we want to find the reflection of the point with respect to the line. Okay, so that's also understandable, yes? If you have a line, so if I have a line in a space and I have a point, for example, this is your line, this is the point. So what is the meaning of reflection? That's as normal. So you need to find a way to draw a perpendicular line from that point that intersects this one, and then continue it from the side, just extend it, and then you find the point. So we are supposed to find that. I think that's also very simple if you think. Yes, I want to give you another opportunity. Please solve this one, yes? And I will check your answer against GeoGebra, because that is also another feature in GeoGebra. You can do this immediately. Okay, do you have the answer? Okay, I will wait more.
Alltså det låter ganska vilt.
Okay, come on guys, what happened? No answers.
I think I went in a circle. My arguments.
Yes?
I got an answer, but it seems too weird because I got thirds.
Thirds?
Yeah, 7/3, 4/3, and 1/3.
Why this is weird?
And
So, what are your answers?
x equals 7/3, y equals 4/3, and then
4/3?
4/3,
Yes?
and then z equals 1/3.
1/3. So if you don't mind, let us immediately check it with GeoGebra. That's also good to learn. So, let us check your answer. What about the rest of you? No answers? Okay, let us first check through GeoGebra. Okay, so for example here, I can get rid of all of these. And then of course I want you to read me. What was the line?
So x equals y equals.
I hope, I don't know, let us see GeoGebra understands how to act here. So x equals to?
Y equals to z plus 1.
Equals to z plus 1. Yes, it realizes. Okay, so it's more smarter than I thought. Okay, so this is your line. And then what was the point?
The reflection or the
No, the point, the original point.
1, 2, and 1.
1, 2, and 1. That's the point. So if you want to enjoy this landscape, you can also see what's happening here. And then of course GeoGebra also have this reflection about a line. So you just choose that, choose the point. Okay, are you ready? So that's your answer. Yes, because unfortunately in this graphic tool, the GeoGebra is not capable of giving the exact value unless you go to the CAS view. Might be if we can do it in CAS view in combination with the graphic, we will get the correct answers. But what you say is actually correct, yes? It's 2.33 is 7 over 3, and then the other one is 4 over 3, and the other one is the congratulations. So that's correct. At least you can see this feature also works very nicely in GeoGebra. Okay, so now let me actually go back to... Okay, so... Okay, can you tell me what is your strategy, because your answer is correct. Okay, let me first draw the rough sketch of this problem. So you have a line, wherever it is, but you need to imagine it in a space. But it doesn't matter, by the way. I have drawn it on the whiteboard. Don't get this wrong feeling. If this is the point, if this is the line, the point is here, still I have that plane. But that plane is not a vertical plane, would be an oblique plane, yes? That's another plane. Okay, so this is your point, and this is your line. You are sure that the point does not lie on the line because, for example, x and y coordinates should be the same if this is supposed to be on the line, but they are not. Okay, and then the point that I am going to find is to find this point A prime again. So I drop a perpendicular line from A to the line, which is always possible. And then I extend it to its own length and I get A prime, and I want to find these coordinates. Yes? So now what is your strategy?
So I used a projection vector.
Okay, so how?
I picked a random point B, which was 1.
So I will follow yours because my intuition was a little bit different, but I will also share my way of thinking. So you say that I find a random point. If you want, I can call it B for you. So can you tell me what is your random point?
1, 1, and 0.
1, 1, and 0. It works because 1 is equal to 1 is equal to 0 plus 1. That's correct. So I will take 1, 1, and 0 as you do. Okay, then. Of course, I don't know this is the correct picture. I don't know. Might be this point is there. All right. So your reasoning should be independent of real location because that is just rough sketching. Yes, there is no guarantee that this is the real picture. Okay, but that's more understanding. Okay. And then?
So then I calculate the projection vector, so I need the vector between B and A.
Okay, so you draw this vector BA. So what is BA? BA I can calculate is A minus B, the final point minus the initial point. But the final point is 1, 2, 1. So 1, 2, 1 minus the initial point that we got it 1, 1, 0. So if you calculate, it becomes 0, 1, and 1. So you have the components of your vector, and then you project it onto this line. But of course, I cannot project on a line, but I can project the vector onto another vector. That vector is clearly the direction vector of your line. It is in canonical form, a standard canonical form. So if I ask you what is D, again, I am drawing D here, but no one knows that this is real or not, yes? Even this is in this direction or in that direction. The good point is that the projection vector itself is sensitive to these changes and it will take care of everything. So you really don't need to be worried about those things. If you remember, we discussed about this before. So I write this direction vector. The direction vector are the denominators in the standard canonical form, which is 1, 1, 1. And you project BA onto D. And then according, if you have the formula in your head, this is the formula, yes? Okay, so then BA is this, I dotted here. So 0 times 1, 0, 1 times 1, 1 times 1, 1. I add them, it becomes 2. The norm of D squared is 3, yes? And then multiplied by D is 1, 1, 1. Am I allowed to rescale it by multiplying by the reverse? No. Because here I'm supposed to find the length. Is that, by the way, can I do that?
I think you could multiply.
Yeah, I think this is not length here, yes? In that case, that the projection vector, if I increase the length or, I don't know, decrease the length, it doesn't matter for your purpose because you are supposed to find what? Okay, can you tell me what you are supposed to do?
So we're supposed to find the actual length between point B and intersection point.
Okay, but so do we know intersection point now?
Well, we know the length D.
Okay. So might be you got the wrong, so you got the correct answer, but that is not correct, is it? Yes, 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 that's correct, sorry.
Yeah.
Yes, that's correct. So what you are saying is that because the projection, so I cannot rescale it.
Well,
In the way that you are doing, I think, what you are going, may you please repeat it again?
Oh, wait, no, I multiplied into the 3 in the...
Okay, but, so can you continue? I don't see your point yet, because I want to find the coordinates.
Yeah, but okay, so then we know the projection vector there, and so I took then the vector BA minus the projection vector. Like
That is correct.
I'll do it before.
That is correct.
We did that yesterday.
So you got that one. So I mean, BA minus the projection vector. So the projection vector is not, yes, the projection vector is here. Is from here to here. You are right. So I was a little bit careless. So this is D. This small one, first one is D. I don't know if this is smaller or might be it is even longer. We don't care. D is somewhere here. Even if it is in the wrong direction, I don't care. But then anyway, the projection vector is this length. Yes? And then what you are doing, I don't think you can rescale it then. Because you want, okay, so you have to calculate, so you want to find this one. Yes? Okay, tell me what to do.
So then took the BA vector minus the projection vector.
Okay, the projection vector. So it means that I cannot rescale it. D. So this BA is 0, 1, 1 minus the projection vector. The projection vector is 2/3. I multiplied in 2/3, 2/3. And then subtract it. It becomes negative 2/3. And then it becomes 1/3, another thirds. Yes? So that is BA minus. So what you got is this orange vector for the time being. This is the orange vector. Okay, then?
So then we have the vector between the intersection point and A.
Yes?
So then we can calculate the intersection point. So we can then do, or wait, we can do that easier.
No, I don't see. I want to wait for you still.
Because I followed the same as the last problem when you tried XH.
No,
I
so,
could just,
so no, because you want to reach to this point. So far, you got the components, not coordinates, the components of this orange vector.
Oh, you can just look.
Yes? But how did you get those numbers which are correct?
So we know the general the vector between the intersection point and A. So we can just say that minus 2 over 3 equals 1 minus xh, and go with that part.
No, I don't see why that is correct. Might be that's a coincidence. Because I don't know anything about this. If you don't tell me how can I get these coordinates, I don't know. But we can find the coordinates, but I want to see it exactly how. I know how to find the coordinates.
Yeah, but we can find the coordinates from the vector we just made.
We just made.
Yeah.
This projection vector or the, okay, so how?
Since we know the vector numbers between the intersection point and A.
Okay, now I understand what you say. So let me write this H. Yes? So this is HA. Agree? Okay, so we know HA. So now you want to find H.
Yeah.
That is possible. Yes, that's correct. Because instead of AH, HA on the one hand is equal to that. What is this you are saying? On the other hand, you can write it the final point minus the initial point. Yes? So the final point is what? Is A, which you know it. What is that? 1, 2, and 1. Minus the initial point that you don't have it. So let us write XH, YH, and ZH. Yes? But the result you know. The result is supposed to be minus 2/3 by the calculation. Very nicely you mentioned. And then you see that I can find all these numbers that I need. Yes, that is correct. And that was not a coincidence at all, sorry. So I was thinking that you are confusing the components with the coordinates. Okay, so now we can do it in our head, yes? So for example, 1 minus x of h is supposed to be minus 2/3. So x of h becomes what? 1 plus 2/3, which is 5/3. Yes? And then 2 minus yh is supposed to be 2 minus 1/3. And what is the answer? This means that it is 1/3. And then I have to find a yh. So yh is 5/3 again, yes? And then you calculate z of h. So 1 minus z of h is 1/3. So this means that z of h is 2/3. So this means that finally you were able to find this h, which is 5/3, and then 5/3 again, and then 2/3. Yes? And then the problem is as before. I have this point, I have the middle point, I want to have this point. For example, let me calculate one of them. So 5/3, which is x of the middle point, is equal to the average of the x's of these 2 points. X of a we already know is 1, x of a prime is unknown, divided by 2. So you multiply, it becomes 10/3. You subtract 1 from it, so xa prime, as you predicted correctly, is 7/3, and then you can continue the rest, you will get the answer. Yes? That's correct. But any other alternatives? But let me tell you something else. But now that you solve it in this way, which is a very, very good way, using vectors effectively, why we couldn't do it in a different way? Because if I were you, I would multiply this vector by -2.
Okay.
Then what will happen? It becomes this vector. Yes? Okay. No, that's not a very good thing. That's also possible. Then I would add this vector to this vector. I will come to this point. But it is not the point. It becomes this vector. And again, of course, you have to subtract. It's very, very good, by the way, this because you are using vectors. The good point about vectors, here in high school, we are working in 3 dimensions. Okay? So we can imagine lines and planes. So the solution that I want to present is in a high school way. But this is in higher dimensions. You will see later that we can also talk about dot products in 4 dimensions and 5 dimensions. Yes. So this means that this idea will actually continue to survive if you go to higher dimensions. Then you can, for example, you can find the reflection of a point with respect to a hyperplane or something like that in 4 dimensions. But you will come to that later. But that is quite good. But more geometrically, can you see another way? The way that I did the first problem, just very intuitively. It's a very, very nice way. It's an abstract way, and I really like it. But what about something like this? This time, I have this line, and I have this point somewhere else. So what I do, I draw a perpendicular plane. Yes? I draw a plane that passes through this, and is perpendicular to my line. Yes? And then what you get, the intersection point is again the point that you need. Isn't it true? Okay, now let us think about it. So, can you tell me how to write? So this L, you know the direction vector. So what is the direction vector? It's 1, 1, 1. But this direction vector plays the role of the normal vector. It's extremely simple then. So what can I write for this one? I have a point, 1 to 1. So you remember this is the standard formula for writing an equation of a plane, isn't it? So A, B, and C are 1, 1, and 1. X minus X node, the X coordinate of A is 1, plus 1 times Y minus 2, plus 1 times Z minus 1 is equal to 0. So it becomes X plus Y plus Z is equal to 4. This is the equation for my plane. And then I am looking for intersection, because that's the intersection of two objects, again as before. So what I do, my equation of the line is x equals to y is equal to z plus 1. And my equation of the plane is this one. What I need is to solve this system. Again, 2 equations here, 1 equation here, 3 equations, and I have 3 unknowns. So I can solve it easily. For example, I decide to write everything in terms of x. X is x, y is also x, but z is x minus 1 is equal to 4. So 3x is 5, x is 5 over 3. And 5 over 3 was the number that you predicted here. You calculated here, not prediction. Yes? And then if x is 5 over 3, what is y? Y is equal to x. So what is z? Z is y minus 1. And that 5 over 3, 5 over 3, 2 over 3 is exactly the same. So, I mean, the calculation was more straightforward, but of course we are using geometry. We will lose this idea when we go to higher dimensions, but this idea will still work. And that's the reason that I want you to learn about vectors quite good. So I will not continue this because the rest of it is as before. Just this one plus that one. You need to think why I couldn't solve the problem. Yes? If you couldn't. Okay, so I think we have to stop here, but I changed my mind. I will continue with the line a little bit more. Yes, because this will be necessary for you in actually quite a short time from now. Any questions? Thank you. And so, by the way, one problem is left. Work on it. Yes? One problem is left. Work on it. These are extremely simple problems. Next time, remind me, if I forget, to start with this problem.